So, the goal of this lecture will be to cover the following topics. We will start with a quick recap of what we saw last time, which is questions about the data model. It's the basic assumption in statistics and the notion of estimators that we define. Okay, next we will recap how we defined the bias and variance of estimators. This turns out to be a very interesting topic, and a lot of statistics focuses on understanding bias and variance of different estimators. Okay, we'll also come upon a very related term which I'll call the mean squared error, which turns out to be quite related to the variance. Okay, and then we will do a couple of case studies. So the first one, I'm doing this first because I think it illustrates. I mean, if we do only the second one, we end up, maybe some of you may have confusion about the distribution of the estimator versus the original distribution. That tends to be a point of confusion. So let's start with a much simpler distribution, which is just the Bernoulli, and we'll see how you estimate the heads probability and do a thorough case study of the bias and variance in that example. Okay, and then we will look at this question. So now you have two parameters, mu and sigma, and let's say you have a bunch of samples that you draw from a Gaussian with parameters mu and sigma. How do you estimate these parameters? What are the bias and the variance of these estimators, and so on? And then we'll take a slightly different view of estimation, where instead of coming up with an explicit formula for the estimator, we will actually write down a function which I will call the likelihood, and we'll try to find parameters so that the likelihood is maximized. Okay, so that's the rough topic. So we may not get to the last topic, but we will end up doing these things. Okay. All right. So let's start with a very quick recap. So as I was saying, so the basic assumption in statistics is that you have some data, let's call it x1, x2 up to xn, and the assumption is that these are generated independently from some distribution D. Okay, these are independent draws from some distribution D. You can also view them as independent random variables, and these are some realizations of these random variables that I have, like I spoke about last time. Okay, so essentially data comes from a model. Okay, so this is the basic assumption in statistics, and now the questions that we would like to answer are basically, if you have data, how do you estimate parameters of the model? Okay. So the estimation problem is given data, find the parameters of the model. Okay. And we said that estimation problems are usually solved by defining what are called estimation functions, or simply estimators. Okay, so what is an estimator? So an estimator is an example of a statistic. Okay, so it's a function or a statistic t of x1, x2 to xn. This just basically means it's a function, some function. Okay, So a statistic T is supposed to estimate some model parameter. Okay, so a model parameter theta. Okay, so this means a parameter. Okay, so this is how we defined an estimator, and the canonical example was called was the empirical mean. So this we also called it the mean estimator, and this was simply the function x1 plus x2 so on up to xn divided by. Okay. So this is a very simple estimator, and we said that, for instance, in the case of Gaussian, if xi's were samples from a Gaussian, we can hope that this is actually a good, this provides a good estimator, a good approximation to mu with a good probability. Okay. And what we also said last time is that estimators only can only hope to work in a probabilistic sense. Okay, so estimators are good only in a probabilistic sense. Okay, so the example we'll see today will really drive this point home. Okay, so so the idea here is that sometimes we may be unlucky, and let's say I compute this mean estimator, you may end up with a bad estimate for the mean. Okay. The hope is that that will only happen with a small probability. Okay, and that's where the variance of the estimator comes in. Okay, so without further ado, so let me not go into the definitions of bias and variance right away, but let's take the first case study. Okay, so case study 1, estimating parameters of a Bernoulli. Bernoulli distribution. Okay, so what is the Bernoulli distribution? This is a very simple one. So Bernoulli P. So this takes it's a distribution which is only over 0 and 1, and it takes a value 1 with probability P, takes value 0 with probability 1 minus P. Okay, so that's the Bernoulli random variable, or the Bernoulli distribution. Okay. Now what I'm saying is, suppose I give you n, suppose we have given n samples from this distribution. Okay, so I will call these x1, x2 to xn. Okay, so these are n samples from this distribution. Okay, so maybe I should be a bit careful here and and try to distinguish capital X from small x. Okay, so so these are actually, so each xi is a realization of this random variable x1. So when I write capital X1, x2 up to xn, these are actually random variables, and each is these are all distributed as Bernoulli P and all independent. So this is why we did this whole notion of independence of random variables right before we delved into the statistics parts of the course. Okay, so this is the setup. Okay, so we are given n samples. These are actual values. These are like, let's say I get a 0, I get a 1, 1, 0, 0, 0, 1, something like this. So you have n such samples, and right. Okay, and now your goal is to find the p. Okay, so now the goal is to estimate p. So the most natural kind of most natural estimator intuitively, right? It is the fraction of ones, number of ones divided by total number. Samples. Right, so this intuitively is like the most natural estimator, right? Because each one is each one is 0 or 1, and you are interested in the probability of it being a 1. Okay. So this is the most natural estimator for this quantity, and if you see, this is exactly the same as sum of I going from 1 to n of xi divided by n, okay, which is basically the mean estimator. Okay. So this is exactly what we are trying to estimate. Okay. Okay. And now the question is, how good is this estimator, right? So the question is, how good? Okay. So let's see a few examples. Okay. So example, let's consider n equals 2. Okay. And for simplicity, assume that for concreteness rather, let's assume that p is some value. So let's say it is 0.1. Okay. So there's a 0.1 probability of seeing a heads. So roughly 1/10 of the observations will be heads. Okay, will be ones. Okay, so this is the first concrete example that we will consider. Okay, so let's see what happens. Okay, so if n is 2, means that you get two samples, right? So you get either 1 1, or you get 1 0, 0 1, or 0 0. Okay. So these are all the choices of x1 and x2. And there's some probabilities of each one. So this one, the probability is 0.1 times 0.1 and so on. Okay. But note that you don't know these probabilities because we don't know p. Okay, so these are unknown to us. Okay. And all we see is one of these events. Okay, so we see one of these outcomes. Okay. Now what we are saying, so what is the value of this estimator, right? So let me call this estimator as y. Okay, so y is x1 plus x2 by 2. Okay, so this is the estimator, the same as the t that we used before. Okay, so what's the value for this estimator, right? So we don't know these probabilities, so let me erase them. Let me write down y, the value of y in each case. Okay, so if so this is the value of y. So you get a value of 1 in this case, you get a value of a half, value of half, a value of 0. Okay. And if you think about it, so these are all the values, these are all the possible outputs that your estimator can produce. Okay. Note that the true P, which is 0.1, is not one of these values. Right? So the possible outputs are 1, half, and 0. Okay. And 1 happens like we observed before with probability 0.01. This happens with 0.09, this happens with 0.09, this happens with probability 0.81. Okay. So I'm just working out probability. Okay, so this is 0.1 times 0.1, this 0.1 times 0.9, and so on. Okay. So if you look, if I ask you how is y distributed, okay, so this is actually a simple question, right? So we y will be 1 with this probability, y will be a half with probability 0.9 plus 0.09 because these are both half. Okay, so you will say that y is 1 with probability 0.01, it is half with probability 0.18, it's 0.09 plus 0.09, and it's 0 with probability 0.81. Okay. And like I observed before, the y is actually never equal to 0.1, which is like the true value of p. Okay. But if we follow this estimator, you're going to get one of these values. Okay. Now what you can observe is that, so this is now the distribution of y. Okay. So this is why I wanted to talk about discrete random variables, because note that the distribution of y really has nothing to do with the distribution of each xi, right, which was a binary 0 1 random variable. This is now, it takes a bunch of values, each with certain probability. Okay, so if you draw the histogram for y, by that I mean imagine doing this experiment several times, and each time I get a y, and I plot how many times I see a 1, how many times I see a half, how many times I see a 0. So many times you will see a value of 0, few times you will see a value of 1 of a half, and value for 1 will be very low. Okay, so this is how the histogram or the probability mass function of y looks like. Okay, so the point I'd like you to notice here is that y is an estimator, and this is some function of these original random variables x1, x2, and this itself has some distribution. Okay, and this distribution looks like this. Okay, so now, so note that this, at least with n equals 2 and p equals 0.1, is a pretty lousy estimator, right? Because with a pretty high probability it is equal to 0, okay, with like 0.81, and there the error is like 0.1, so the true p was 0.1, right? And this estimator is actually never equal to 0.1. Okay? But note that if I look at the expected value of y, okay, so y is now a discrete distribution, and this is how it's distributed. If I look at the expected value of point y, so of y, this would be, how do you compute the expected value of a discrete random variable? You look at the probability times the value and you sum them up, right? So it's 1 times 0.01 plus half times 0.18 plus 0 times 0.81. Now what is this quantity? Lo and behold, you end up with the value of 0.1, okay, because this is 0.01, this is 0.09, okay, so this times this is 0.09. So this ends up being 0.1, which is actually equal to P. So the expected value in expectation, this y is actually a pretty good estimator, right? So this y, the expectation of this estimator, turns out to be the right value, which is P. Okay, and this is exactly what I defined to be an unbiased estimator, right? So y is an unbiased estimator for P. Okay, because the expected value of this variable is actually equal to P. Okay, so this is an unbiased estimator. But now what is the, but we are also interested in two other quantities. Okay, so what is the typical error, of the estimate? Okay, and what is the variance of the estimate? Of the estimate. And these, the reason I'm doing this separately is because I want to highlight that these are actually two different quantities. Okay. So the typical error is, or even typical squared error. So we know that y is distributed like this, right? So y is 1 with certain probability, y is half with certain probability, and 0 with certain probability. Okay. Now, while the true value, which is the p, which is the value that we care about of the true value of the parameter, is always away from y, like we observed before. Okay. So suppose I look at, let's call this quantity a and let's call this b. Okay, so now I'm talking about a now. So I am interested in y minus p whole square. Okay, so y is a random variable. Now y minus p whole squared is also a random variable, and this value equals 1 minus p whole square with probability 0.01. Okay, this is equal to half minus p whole squared with probability 0.18. It's equal to 0 minus p whole squared with probability 0.81. And why is this? Because y takes value 1 with probability 0.01, half with probability 0.18, and so on. Okay, so this takes value which is like this. Okay, and you can plug in p equals 0.1, and this simplifies to basically, this is 0.9 square, so this is 0.81 with probability 0.01. This is 0.5, so this point, these numbers don't really matter, so, and 0.01 with probability 0.8. Okay, so what I'm now asking is, what is the typical or the expected squared error of this estimate, right? So what is the expectation of this quantity? That's what I want to know. So it's the expected value of y minus p whole square. Okay. And note that you can now compute this, right? So this is just another random variable, so it will be this times this, plus this times this, plus this times this. Okay. So let me not do that because it's just some calculation. Moreover, it's not terribly important. Okay. So this quantity though, so the expected value of y minus p whole square, this quantity is called the expected mean squared error expected squared error or the mean squared error of the estimator. Okay, so this is what we define as the expected squared error of the estimator. The variance of the estimator is a little bit different. The variance of the estimator, on the other hand, is simply defined as you view the estimator as a random variable and you find its variance. Okay, so it is the expected value of y minus the expected value of y whole square. Note that this is exactly the variance of y. Okay, so if treating y as a random variable. Okay, so what have we defined so far? So far we have defined the notion of a variance, the notion of the expected squared error of an estimator y. Okay, so next video I'll show you two things. One is that these two quantities are the same if y is an unbiased estimator. That will become very easy in our example. We already saw that y was an unbiased estimator. So in this case both are the same, and we will also see how these two relate in general.